Right now, sitting wherever you are moving, not just breathing, not just existing quietly on a chair or a couch, but physically hurtling through space at roughly 670,000 miles per hour. That is the speed at which Earth carries you around the sun. And the sun itself is not standing still either. It is dragging you and everyone you have ever known in a long, slow orbit around the center of a galaxy so large that light, the fastest thing in existence, needs 100,000 years just to cross it. That galaxy, the Milky Way, contains something like 400 billion stars. And here is the part that tends to break people's sense of scale once they actually sit with it. Our galaxy, home to those 400 billion stars and however many planets orbit them, is just one of an estimated 2 trillion galaxies scattered across the part of the universe we can currently observe. Not 2 trillion stars, 2 trillion galaxies, each one containing billions or hundreds of billions of stars of its own. We are going to walk through exactly how astronomers arrived at these numbers, what they actually mean, and how the scale of the universe keeps expanding the moment you think you have wrapped your head around it. This is not going to be a string of scary superlatives. It is going to be the actual reasoning, the actual measurements, and the actual physics that force scientists to keep revising just how big reality really is. Start with something familiar. Stand in the middle of a large city at night and look at the skyline stretching in every direction. Lights fading into darkness at the horizon. Now stretch that same density of light across an entire country, then across an ocean, then wrap it around the entire planet. You have just built, in your imagination, something roughly the size of a large city grid extended across the globe. Multiply that distance by around 6 billion, and you arrive at something approximating the width of our galaxy. Astronomers did not guess this number. They measured it using a combination of techniques that include tracking the parallax, or apparent shift in position, of nearby stars as Earth orbits the Sun, and calibrating that against the brightness and pulsation patterns of certain variable stars whose true luminosity is well understood. Layering these methods together, the Milky Way measures out to about 100,000 light-years across. Since 1 light-year is roughly 6 trillion miles, the disk of our galaxy spans something on the order of 600,000 trillion miles from one edge to the other. That number is difficult to hold in your head, and it is only the first rung on a very long ladder. Every star you can see with your naked eye on a clear night, without exception, belongs to our own galaxy. The faint band of hazy light that stretches across a dark sky, often called the Milky Way itself, is literally the edge on view of our own spiral disk, seen from inside it. We are not looking at the galaxy from outside, the way you would look at a photograph of a spiral galaxy. We are embedded inside one of its spiral arms, roughly 26,000 light-years from the galactic center, looking out through the plane of the disk the same way you might look sideways along a dinner plate. From this position, astronomers can observe active star-forming regions, where clouds of gas collapse under gravity to ignite new stars, alongside the remnants of stars that have already died, sometimes in supernova explosions that scatter heavy elements like carbon, oxygen, and iron back into the surrounding gas. This matters more than it might first sound. Every rocky planet, every trace of carbon in a living cell, ultimately traces back to material forged inside a star that lived and died long before our solar system existed. Here is where the numbers start to become genuinely strange. Light is the fastest thing in the universe, moving at about 670 million miles per hour, fast enough to circle the Earth roughly 7.5 times in a single second. And yet, Even at that staggering speed, light takes 100,000 years to cross our galaxy from one side to the other. That means the light reaching your eyes tonight from a star on the far side of the Milky Way left that star before modern humans existed in anything resembling our current form. This creates a strange consequence for how we actually observe the galaxy. Nearby stars show us light that left fairly recently in astronomical terms. Stars near the galactic center show us light that departed tens of thousands of years ago. Every image of the galaxy, whether a photograph or a computer-generated map, is really a patchwork of different moments in time layered on top of each other. We never see the galaxy as it exists right now. We only ever see a composite of its recent past, smeared across tens of thousands of years. It gets even stranger when you factor in rotation. The Milky Way is not a static structure. It spins, with our solar system completing one full orbit around the galactic center, roughly every 225 to 250 million years. During the 100,000 years it takes light to cross the galaxy, the galaxy itself continues rotating, meaning the structure is subtly reshaping itself while that light is still in transit. The galaxy you are picturing in your head, frozen in a single instant, does not actually exist. It is always mid-motion, always slightly different from the last snapshot. This has a practical implication for the question of contacting other civilizations. If any exist elsewhere in the galaxy, radio signals travel at the speed of light, the same speed limit that governs everything else. If an advanced civilization on the opposite side of the Milky Way sent a message today, it would take 100,000 years to arrive. A reply would take another 100,000 years to return. Any conversation across galactic distances is not a conversation in any meaningful sense. It is closer to two civilizations leaving messages in bottles for descendants. They will never meet. Now turn to something you can actually see with your own eyes. Step outside on a clear night and find the brightest star in the sky, Sirius. It is genuinely a bright object, roughly 25 times more luminous than our own sun. Bright enough that several ancient cultures built calendar systems around its yearly reappearance. It looks close. It is not close, not in any way that matters to human intuition. Sirius sits about 8.5 light-years away, which works out to roughly 50 trillion miles. If you tried to drive there at highway speed without stopping, the trip would take around 800,000 years, and Sirius happens to be one of the closest stars to our solar system. Across the wider galaxy, the average distance between neighboring stars is closer to 4 light-years. To get an intuitive sense of what that means, imagine shrinking the sun down to the size of a basketball. At that scale, Earth would be a grain of sand orbiting about 26 feet away, and the nearest star system would be another basketball sitting in a different city entirely. Almost everything between those two basketballs is empty space. This is the actual texture of a galaxy, not a crowded field of adjacent suns, but a mostly empty volume punctuated by isolated points of light, separated by staggering gulfs of vacuum. This spacing is also part of why interstellar travel and interstellar contact with other civilizations remains so difficult even in principle. Even traveling at the speed of light, a journey to the nearest star system takes years. Using the propulsion systems humanity currently has, a comparable trip would take tens of thousands of years. If other civilizations exist on planets orbiting other stars, they are separated from us and from each other by exactly the same gulfs of space and time that isolate us. The universe does not make loneliness a human problem. It is a structural feature of the way galaxies are built. So how many stars actually populate this structure? Estimates place the Milky Way's stellar population somewhere between 100 billion and 400 billion stars, with the uncertainty coming from the fact that thick clouds of interstellar dust obscure large portions of the galactic disk from direct observation, especially toward the crowded galactic center. Infrared telescopes, which can see through dust that blocks visible light, have helped narrow this range, but a precise count remains elusive. Even the conservative end of that estimate, 100 billion stars, is difficult to intuitively process. If you tried to count them one at a time, one star every second, without ever stopping to sleep or eat, the count would take more than 3,000 years for the low estimate alone, and closer to 12,000 years for the higher estimate of 400 billion. Each of those stars is a nuclear furnace, and our own sun alone converts about 4 million tons of matter into pure energy every single second through nuclear fusion. Multiply that kind of output across hundreds of billions of similar reactions occurring simultaneously throughout the galaxy, and the total energy output of the Milky Way dwarfs anything produced on Earth by factors that require scientific notation to express clearly. Despite all of that, the Milky Way itself is considered a fairly ordinary, medium-sized spiral galaxy. Some galaxies contain more than 1 trillion stars. Others, the so-called dwarf galaxies, contain only a few billion. And our galaxy is not an isolated island either. It exists inside a small cosmic neighborhood, gravitationally bound to roughly 50 or so other galaxies, in a structure astronomers call the local group. The local group spans about 10 million light-years and is dominated by 2 large spiral galaxies, our Milky Way and the Andromeda Galaxy, with a collection of much smaller dwarf galaxies orbiting around them, somewhat like smaller planets orbiting 2 dominant stars in a binary system. The most visible of these dwarf companions, at least from the southern hemisphere, are the large and small Magellanic Clouds, sitting roughly 160,000 and 200,000 light-years from us respectively. These smaller galaxies are not simply passive neighbors. Observations show that the Milky Way's gravity is slowly stripping gas and stars away from the Magellanic Clouds, a process that has been ongoing for billions of years and is gradually feeding material into our own galactic disk. Galaxies, in other words, are not static islands drifting through empty space in isolation. They interact, they pull material from each other, and over long enough timescales, they merge. Which brings us to Andromeda. Point yourself toward the constellation that shares its name on a clear autumn night, and you will see what looks like a faint, unremarkable smudge, easy to miss if you are not looking for it. Through a telescope, that smudge resolves into an entire galaxy, containing more than 1 trillion stars of its own, roughly 3 to 4 times the stellar population of the Milky Way, and spanning about 220,000 light-years across, more than double the diameter of our own galaxy. Andromeda is approaching us. Precise measurements, based on the Doppler shift of its light, show it closing the distance at around 250,000 miles per hour. Current models, built from decades of tracking its trajectory and mass, predict that in roughly 4.5 billion years, the Milky Way and Andromeda will begin merging, a process that will unfold over billions of years and eventually produce a single, larger elliptical galaxy that astronomers have informally nicknamed Milkomeda. Despite the scale of that collision, individual stars are extremely unlikely to physically collide with each other. The spacing between stars, that basketball in one city and a second basketball in a different city, is so vast that even when 2 galaxies merge, the stars themselves mostly slide past one another, pulled into new orbits by the combined gravity of both systems rather than smashing together directly. Our own solar system will likely survive the merger intact, though it may end up flung into a very different orbit. gazing up at an unfamiliar arrangement of stars. Here is a detail worth sitting with. The light reaching us from Andromeda tonight left that galaxy about 2.5 million years ago, long before modern humans existed as a species. We are seeing Andromeda not as it exists today, but as it existed when early hominins were first experimenting with stone tools. The galaxy that is actually racing toward us right now, in this present moment, may look nothing like the version we can currently observe through a telescope. We simply have no way to see it as it exists now. Every observation of deep space is, by necessity, an observation of the past. Zoom out further, past our own local group, and you encounter clusters of galaxies. Structures where thousands of individual galaxies are bound together by gravity, so intense that it noticeably distorts the surrounding fabric of space and time. The nearest major cluster, called the Virgo cluster, contains more than 1,000 galaxies and sits about 54 million light-years from our local group. Galaxy clusters present a genuine puzzle that took decades to resolve. When astronomers measured the speeds at which individual galaxies move within these clusters, they found velocities far too high, in some cases exceeding 1 million miles per hour. For the visible matter, stars, gas, and dust, to hold the cluster together gravitationally. By the physics of visible matter alone, these fast-moving galaxies should have flown apart and scattered across space. Billions of years ago, the resolution to this puzzle was the discovery of dark matter, an invisible form of matter that does not emit, absorb, or reflect light, and can only be detected through its gravitational effects. Within galaxy clusters, dark matter appears to outweigh visible matter by roughly a factor of 10 to 1, providing the additional gravitational glue needed to hold these structures together despite the extreme velocities involved. One of the clearest pieces of evidence for dark matter comes from an object astronomers call the Bullet Cluster, the result of a collision between two galaxy clusters moving at speeds exceeding 10 million miles per hour. During that collision, the visible, ordinary matter, mostly in the form of hot gas, collided and slowed down, the way two clouds of smoke might collide and mix. But mapping of the gravitational lensing, the way the collision bends and distorts the light of more distant background galaxies, revealed that most of the mass in the system had passed straight through the collision, essentially undisturbed, completely separated from the visible gas. That separation is exactly what you would expect if dark matter exists and interacts with itself far more weakly than ordinary matter does. Galaxy clusters also host gas heated to staggering temperatures, often around 100 million degrees, hot enough to strip electrons from their atoms entirely and produce a glowing plasma that radiates in X-ray wavelengths detectable by orbiting telescopes. Remarkably, this superheated gas, spread thinly between the cluster's galaxies, contains more total mass than all of the cluster's galaxies combined, even though it remains completely invisible to ordinary optical telescopes. Clusters themselves are not the largest bound structures we know of. Zoom out again, and clusters organize into even larger groupings called superclusters, some spanning hundreds of millions of light-years and containing tens or even hundreds of thousands of individual galaxies. Our own local group belongs to one of these, named Laniakea, a Hawaiian word meaning immeasurable heaven, which spans roughly 500 million light-years and contains more than 100,000 galaxies. Laniakea was mapped by tracking what astronomers call the peculiar velocities of thousands of galaxies, meaning their motion beyond the general expansion of the universe itself. Even as cosmic expansion pushes distant galaxies apart from one another, Gravity still pulls nearby galaxies toward regions of higher mass density. By carefully measuring these small deviations in motion across a huge sample of galaxies, researchers were able to reconstruct the boundaries of the larger structure our galaxy belongs to, revealing that the Milky Way and millions of neighboring galaxies are all slowly streaming toward a region of unusually high mass concentration. That region, nicknamed the Great Attractor, appears to contain the combined mass of tens of thousands of galaxies, though a large portion of it lies hidden behind the dust and gas of our own galactic plane, making it difficult to observe directly. Its gravitational pull nonetheless shapes the motion of galaxies across hundreds of millions of light-years, acting as one node in an enormous, only partially mapped web of matter, because superclusters are held together by gravity that is comparatively weak relative to their own enormous size, and because dark energy is actively working to push space apart everywhere. Superclusters are considered less like solid, permanently bound structures and more like loose, temporary associations. Some regions within them will continue collapsing inward under their own gravity, while other, more distant regions will likely be pulled apart entirely as cosmic expansion continues. Zooming out to the largest scale astronomers can currently map, something surprising emerges. Galaxies are not scattered randomly through space. They trace out a vast, three-dimensional structure that resembles a web, or a sponge, or foam, depending on which metaphor a given astronomer prefers. This structure is generally referred to as the cosmic web, and it appears to be the largest scale organizational pattern in the observable universe. The cosmic web has four broadly recognized components: dense nodes, where galaxy clusters form at the intersections of multiple structures; filaments, long thread-like structures stretching across hundreds of millions of light years that connect nodes together and channel matter along their length; sheet-like walls, formed where filaments intersect and flatten into broader structures; and finally, cosmic voids, enormous regions containing very little matter at all, occupying the spaces between the filaments and walls. These voids are genuinely close to empty. One of the first identified, called the Boat's Void, spans roughly 330 million light-years across and contains only a few dozen known galaxies, an almost unthinkably low density for a region of that size. Voids collectively make up a large majority, on the order of 80%, of the total volume of the universe, even though they contain only a small fraction of its total matter. Current models suggest voids form naturally as matter drains toward denser filaments and walls during the early stages of structure formation, rather than through any kind of explosive event. Even the largest solid structures known, essentially cosmic-scale walls formed where filaments intersect, are difficult to reconcile with older theoretical expectations about how large a bound structure should be able to grow. The Sloan Great Wall, mapped through a large-scale galaxy survey, spans roughly 1.3 billion light-years, while an even larger structure identified through mapping gamma-ray bursts, called the Hercules Corona Borealis Great Wall, appears to stretch across roughly 10 billion light-years, so large that light takes more than a tenth of the current age of the universe just to cross it. The existence of structures this large continues to be debated among cosmologists, since some models of large-scale structure formation struggle to explain how anything could grow quite this big within the current age of the universe. To actually count galaxies across the observable universe, astronomers have relied heavily on what are called deep field surveys, essentially pointing a telescope at a single, tiny, apparently empty patch of sky and leaving the camera's shutter open for an extended period, sometimes many days of cumulative exposure time. to collect every faint photon arriving from that direction. The most famous of these, produced using the Hubble Space Telescope, combined roughly 800 separate exposures over about 11 days of total observing time, covering a patch of sky smaller than a grain of sand held at arm's length. Within that tiny patch, astronomers identified more than 10,000 galaxies, each one containing billions of stars of its own, extrapolating that density across the entire sky. Combined with additional data gathered more recently by the James Webb Space Telescope, current estimates place the total number of galaxies within the observable universe at roughly 2 trillion. Written out fully, that is 2 million individual galaxies. If you tried to observe just one galaxy per second without pausing, it would take you about 63,000 years to work through the entire count. Multiplying that galaxy count by a conservative average of 100 billion stars per galaxy produces a total stellar population on the order of 10 to the 24th power individual stars, a number that comfortably exceeds the total count of grains of sand on every beach and desert on Earth combined. Scientists estimate Earth's beaches alone contain somewhere around 7 quintillion grains of sand, a number with 18 zeros. The observable universe appears to contain meaningfully more stars than that, and every one of these individual pieces of context. Our galaxy, our local group, Virgo, Linear, the entire cosmic web mapped so far, exists inside a boundary astronomers call the observable universe. This is not a physical wall or edge to space itself. It is a boundary defined entirely by light travel time and the age of the universe. Since the universe is about 13.8 billion years old, and light travels at a fixed, finite speed, there simply has not been enough time for light from anything farther away to have reached us yet. Regardless of how sensitive our telescopes eventually become, here is where it gets counterintuitive. Measured directly, the observable universe should have a radius of 13.8 billion light-years, matching its age. But because space itself has been continuously expanding during the entire time that ancient light has been traveling toward us, the true present-day distance to the source of the oldest light we can detect is actually much farther than that. Once you account for that ongoing expansion, the edge of the observable universe works out to about 46.5 billion light-years away in every direction, putting the total diameter of the observable universe at roughly 93 billion light-years. This creates a genuinely strange situation. The most distant galaxies we can currently detect are seen as they appeared when the universe was very young, sometimes only a few 100 million years old. But because space has continued expanding in the time since that light left them, those same galaxies, as they exist right now, in the present moment, have already been carried far beyond the boundary of what we can observe. We are looking at their distant past while their present is permanently hidden from us. Every observer, anywhere in the universe, experiences this same effect. Because the observable universe is defined by light travel time relative to a given location, every point in space is technically the center of its own personal observable sphere. This is not a special cosmic privilege granted to Earth. It is simply a geometric consequence of the finite speed of light, combined with the finite age of the universe. A hypothetical astronomer in a distant galaxy would observe their own version of an observable universe, overlapping with ours in some regions and extending into space that we, from our vantage point, will never be able to see. At the very outer edge of what we can observe sits something called the cosmic microwave background, the oldest light detectable anywhere. For the first roughly 380,000 years after the universe began, matter existed as an extremely hot, dense plasma hot enough that electrons could not stay bound to atomic nuclei. In that state, the universe was essentially opaque, since light could only travel very short distances before scattering off free electrons, much like being inside a thick fog. As the universe expanded and cooled below about 3,000 degrees, electrons and protons combined to form stable hydrogen atoms for the first time in an event cosmologists call recombination. That process suddenly allowed light to travel freely through space rather than constantly scattering, and the universe effectively became transparent almost instantly on a cosmic timescale. The light released during that transition has been traveling through space ever since, and it is what we now detect as the cosmic microwave background, a faint, extremely uniform glow of radiation arriving from every direction in the sky. Because the universe has continued expanding for nearly 14 billion years since that light was emitted, the radiation has been stretched to much longer, cooler wavelengths, now measured at a temperature only a few degrees above absolute zero. Extremely precise satellite measurements of this background radiation have detected temperature variations of only a few millionths of a degree from one point in the sky to another. Tiny fluctuations that are thought to represent the seeds, amplified over billions of years by gravity, from which galaxies and galaxy clusters eventually formed. The cosmic microwave background marks an absolute boundary for anything we can detect using light or any other form of electromagnetic radiation, since no light existed in a form capable of traveling freely before recombination occurred. Whatever happened during the earlier stages of the universe's history, including the extremely brief period cosmologists call inflation, when the universe is thought to have expanded by an enormous factor in a small fraction of a second, can only be studied indirectly through its influence on the patterns we observe in this background radiation, or in principle through the detection of gravitational waves or neutrinos, both of which could theoretically carry information from earlier moments than any light can dot. Now consider the fact that the universe is not simply sitting still, or even simply expanding at a constant rate. In the late 1990s, two independent research teams, studying the brightness and redshift of a particular type of exploding star called a Type 1, a supernova, discovered something that directly contradicted expectations. Instead of cosmic expansion gradually slowing down over time, as the mutual gravitational pull of all the matter in the universe should cause it to do, the expansion appeared to be speeding up. That discovery earned the 2011 Nobel Prize in Physics and introduced the concept of dark energy, a mysterious component now estimated to make up about 68% of the total energy content of the universe, responsible for actively accelerating its expansion. Dark energy behaves very differently from ordinary matter or even dark matter. As space expands, the density of ordinary matter decreases, because the same amount of material is now spread across a larger volume. Dark energy, by contrast, appears to maintain a roughly constant density even as space expands, meaning its total influence actually grows over time, since there is simply more space, and therefore more dark energy than there was before. This is part of why the expansion of the universe continues to accelerate rather than gradually leveling off. The relationship between distance and how fast a galaxy appears to be receding from us is described by what astronomers call Hubble's law, named after Edwin Hubble, who first identified the pattern in the 1920s. Roughly speaking, a galaxy twice as far away recedes about twice as fast, and a galaxy 3 times farther away recedes about 3 times as fast. Extend that relationship far enough, and you eventually reach distances at which a galaxy's apparent recession velocity exceeds the speed of light. This does not violate Einstein's physics, because it is not the galaxy itself moving through space faster than light. It is the space between us and that galaxy expanding, and there is no speed limit imposed on the expansion of space itself, only on the motion of objects moving through it. This has consequences that stretch far into the future of astronomy itself, because cosmic expansion is accelerating. Distant galaxies are gradually being carried across a boundary called the Hubble sphere, beyond which no signal, no matter how powerful, could ever reach them, since the space between us and them is expanding faster than light can cross it. Current estimates suggest the Hubble sphere already contains something like 10,000 times fewer galaxies than the full observable universe, meaning the majority of galaxies we can currently see through a telescope are already permanently beyond any possibility of physical contact or communication, even though their light still reaches us for now. Looking forward, models suggest that within roughly 50 billion years, the Virgo cluster will have receded beyond our observable horizon entirely. Within about 100 billion years, only the galaxies gravitationally bound within our own local group, including the merged remnant of the Milky Way and Andromeda, will remain visible to any future observer standing where Earth once stood. Every other galaxy in the sky will have been carried beyond detection by the ongoing expansion of space. A civilization arising that far in the future, with no access to older astronomical records, might reasonably conclude that their own galaxy is the entire universe, since every other galaxy would already be gone from view, along with the cosmic microwave background itself, by then stretched to wavelengths far too faint and too long for any conceivable instrument to detect. There is genuine scientific debate about how this story ultimately ends. If dark energy's density remains constant, as current data broadly supports, cosmic expansion will continue accelerating gradually, isolating galaxies from each other while individual galaxies, star systems, and planets remain gravitationally intact. Some more extreme theoretical models propose that if dark energy's strength were to increase over time, the acceleration could eventually grow strong enough to overpower gravity even at the scale of individual galaxies, then solar systems, and finally atomic bonds themselves. A hypothetical scenario researchers called the Big Rip, tentatively placed around 22 billion years from now if that particular model turns out to be correct. Current observational data does not clearly favor this scenario over the more modest, steady acceleration model, and researchers are actively trying to pin down whether dark energy's strength is truly constant or subtly changing, using large-scale sky surveys designed specifically to track cosmic expansion with greater precision than ever before. If you find the actual mechanics behind these numbers as fascinating as the numbers themselves, it is worth sticking around, because the next layer of this story gets even harder to intuitively process, and following along, subscribing, or coming back for the next explanation is a good way to keep building this kind of picture, piece by piece. One of the more surprising results in modern cosmology concerns the overall shape, or geometry, of space itself. Extremely precise measurements of the cosmic microwave background allow scientists to test whether the universe is curved, like the surface of a sphere, or perfectly flat, like an infinite sheet of paper. If the universe were noticeably curved, certain patterns in that background radiation would appear distorted in predictable, measurable ways. Instead, observations show that space appears flat to within a very small margin of measurement error, across distances spanning billions of light years. This flatness carries an important implication. A universe that is exactly perfectly flat is most naturally explained, by a total size far larger than the portion we can actually observe, in much the same way that the ground beneath your feet appears flat, even though you are technically standing on the curved surface of a sphere, simply because the Earth is enormous relative to your local field of view. Based on this reasoning, and on the precision of current flatness measurements, some cosmological models place a conservative lower limit on the true size of the entire universe at something like 250 times larger than the portion we can observe, and possibly far larger still, or even infinite, depending on which theoretical model turns out to be correct. This connects to a broader, theoretical framework called cosmic inflation, first proposed in the early 1980s to explain several otherwise puzzling features of the universe, including exactly this flatness, along with the remarkable uniformity of the cosmic microwave background across regions of sky that, without inflation, would never have had time to interact with each other and reach the same temperature. Inflation proposes that in an extraordinarily brief interval, less than a tiny fraction of a second after the universe began, space itself expanded by an enormous factor, stretching a region smaller than a single subatomic particle to a size vastly larger than our entire currently observable universe. A natural consequence of many versions of inflation theory, called eternal inflation, is the idea that this rapid expansion may not have happened everywhere uniformly, or may not have stopped everywhere at the same time. In these models, inflation could still be ongoing in some remote regions, continuously generating new pockets of space, each one potentially settling into its own observable universe, isolated from all the others by the same runaway expansion that separates any two sufficiently distant galaxies today. It is important to be clear about the scientific status of this idea. Eternal inflation and the broader multiverse concept remain genuinely speculative. They are not yet directly testable in the way that, for example, the existence of the cosmic microwave background or the acceleration of cosmic expansion have been directly measured. Some researchers view eternal inflation as a natural, almost unavoidable mathematical consequence of the inflation models that already explain observed features of our universe extremely well. Others remain skeptical, partly because a theory that predicts the existence of regions we can never observe is very difficult to test or falsify using the ordinary scientific method. Several teams have searched the cosmic microwave background for the faint circular imprint that a collision between separate festering, inflating bubbles might theoretically leave behind. And while a handful of candidate signals have been reported, none have held up to further scrutiny as clear, confirmed evidence. It is worth stepping back briefly to appreciate how recently humanity even figured out that other galaxies exist at all. For most of the early 20th century, astronomers were genuinely divided over whether the faint, spiral-shaped smudges visible through telescopes, then called spiral nebulae, were relatively small, nearby clouds of gas within our own galaxy, or entire separate galaxies located at enormous distances, comparable in scale to the Milky Way itself. This disagreement came to a head in a formal scientific debate held in 1920 between astronomers Harlow Shapley and Heber Curtis, each arguing opposing sides of the question. Without a clear resolution at the time, the issue was finally settled a few years later. In 1923 and 1924, when the astronomer Edwin Hubble, using the newly completed 100-inch telescope at Mount Wilson Observatory in California, identified a specific type of pulsating star, called a Cepheid variable, within the Andromeda Nebula. Cepheid variables are useful because their pulsation period is directly related to their true brightness, a relationship discovered earlier by astronomer Henrietta Swan Leavitt. By comparing how bright a Cepheid actually is to how bright it appears from Earth, Astronomers can calculate its precise distance. Hubble's measurement placed Andromeda far beyond the known boundaries of the Milky Way, definitively proving that it was a separate galaxy entirely, and effectively expanding humanity's known universe. Overnight, from a single galaxy to a potentially unlimited number of them. This distance ladder technique, anchored by parallax measurements for nearby stars and extended outward using Cepheid variables and later other standardized techniques for more distant objects, remains the foundation of how astronomers measure cosmic distances today, and refining it further remains an active area of research. In fact, a persistent discrepancy between two different methods of measuring the universe's current expansion rate, one based on the cosmic microwave background and one based on the distance ladder built from nearby stars and galaxies, has produced what astronomers call the Hubble tension, an unresolved mismatch that some researchers suspect may point toward genuinely new physics, not yet accounted for in the standard cosmological model, while others suspect it may eventually be traced to subtle calibration issues in one or both measurement techniques. Large ongoing survey projects are specifically designed to help resolve this tension over the next several years. Return, for a moment, to the question of what might actually be living on all those planets scattered across 2 trillion galaxies. Modern surveys of exoplanets, planets orbiting stars other than our own, suggest that planets are common, with most stars hosting at least one, and many hosting several. If even a small fraction of these worlds, say 1 in a million, happened to develop the right conditions for life, the raw number of galaxies and stars involved would still suggest an enormous number of potentially habitable environments across the universe. And yet the same vast distances that separate individual stars within a galaxy also separate any hypothetical civilizations from one another, by exactly the kind of light travel time delays already described. A civilization thousands of light years away could not meaningfully communicate with us even if it wanted to, since any message sent today would arrive long after both civilizations involved had changed beyond recognition, or possibly ceased to exist altogether. This tension between a universe that appears statistically likely to host life somewhere, and the near total absence of any confirmed evidence of it, is sometimes referred to as the Fermi paradox, named after physicist Enrico Fermi, who reportedly posed a version of the question directly: if the universe is this vast and this old, where is everybody? There is a genuinely satisfying piece of science tying all of this cosmic scale back to something personal. Every element heavier than hydrogen and helium in your own body, the carbon that forms the backbone of your cells, the calcium in your bones, the iron circulating in your blood, the oxygen you are breathing right now, was originally forged inside the core of a star through nuclear fusion, or in the explosive death of a star at the end of its life. Those elements were then scattered into surrounding gas clouds, sometimes over the course of billions of years, before eventually being incorporated into the cloud of material that condensed to form our solar system, our planet, and eventually the atoms that make up your own body. This is not a metaphor. It is a direct, well-established consequence of stellar nucleosynthesis, the physical process by which stars build heavier elements out of lighter ones. And it means there is a literal, physical continuity between the interior of ancient, long-dead stars and the biology of every living thing on Earth. There is something worth appreciating in the fact that a species capable of evolving on a single, comparatively small rocky planet orbiting one fairly ordinary star, in one fairly ordinary galaxy among 2 trillion others, has nonetheless managed to work out the age of the universe to within a small margin of error, measure the distance to galaxies billions of light years away, detect the faint afterglow of the universe's earliest moments, and even directly detect gravitational waves, rippling outward from the collision of black holes more than 1 billion light-years away. Humanity did not evolve with any biological need to understand cosmic scale. Our brains developed to solve much more immediate problems, tracking food, predators, and social relationships within a fairly small physical range. The fact that the same brains have managed to reconstruct the size and history of the observable universe, using nothing but light, mathematics, and an accumulating record of careful measurement, says something genuinely remarkable about what is possible once curiosity is paired with sustained, methodical observation. None of this is settled science in the sense of being finished or closed. Several major open questions remain genuinely unresolved, and they are worth understanding clearly rather than treated as unsolvable mysteries, because active research is underway on each of them right now. The first is the precise nature of dark matter. Its gravitational effects are well established, from the rotation speeds of galaxies to the separation seen in the bullet cluster to the way galaxy clusters bend and distort background light through gravitational lensing. What dark matter is actually made of remains unknown. Leading candidate particles, generally referred to as weakly interacting massive particles, have been searched for directly, using extremely sensitive underground detectors shielded from cosmic radiation. Without a confirmed detection so far, other proposed candidates, called ixions, are being searched for using different experimental approaches entirely. It remains possible that dark matter is not a new particle at all, but instead a sign that our understanding of gravity itself needs modification at very large scales. Though this alternative explanation has struggled to account for the full range of observational evidence as well as particle-based dark matter models do. The second major open question concerns dark energy, the force responsible for cosmic acceleration. Researchers are not yet certain whether dark energy is a fixed, unchanging property of empty space itself, sometimes described using a term Einstein originally introduced called the cosmological constant, or whether its strength varies subtly over cosmic time in ways that current data cannot yet distinguish. A large international collaboration called DESI, the Dark Energy Spectroscopic Instrument, has been mapping the three-dimensional positions of tens of millions of galaxies, specifically to track how the expansion rate of the universe has changed across cosmic history. Some of DESI's early results, released in the past couple of years, have hinted, though not yet conclusively confirmed, that dark energy's strength might be gradually weakening over time rather than remaining perfectly constant, a result that, if it holds up under further data collection, would represent a meaningful revision to the standard model of cosmology that has held for the past several decades. A third area of active investigation involves the earliest galaxies in the universe. The James Webb Space Telescope, since beginning science operations, has repeatedly detected galaxies that appear to be more massive, more structured, and more chemically developed than standard models of early galaxy formation predicted should be possible so soon after the Big Bang. Some of these unusual, compact, extremely luminous objects, informally nicknamed little red dots by the researchers studying them, may represent an early and previously unrecognized phase of galaxy or supermassive black hole growth. Researchers are still working out whether these objects represent genuinely new physics, an underestimated efficiency of early star formation, or some combination of both. And resolving this question is expected to reshape parts of the standard timeline for how the first galaxies formed and grew. A fourth persistent puzzle is the Hubble tension mentioned earlier. The disagreement between two independent methods of measuring how fast the universe is currently expanding One method relies on the cosmic microwave background, calibrated using detailed physics from the early universe. The other relies on the traditional distance ladder, built from parallax measurements, Cepheid variables, and supernova in the more nearby, present-day universe. These two methods currently disagree by several percent, a gap too large to be easily dismissed as measurement error, and too small to be immediately obvious in its cause. Resolving this tension is one of the primary goals of several major current and upcoming surveys, including the Vera Rubin Observatory, a new ground-based telescope designed to repeatedly image the entire visible sky, and the European Space Agency's Euclid mission, along with NASA's upcoming Nancy Grace Roman Space Telescope, all specifically built to gather enormous amounts of additional distance and expansion data over the next several years. A fifth and comparatively newer frontier involves gravitational wave astronomy. Since the first direct detection of gravitational waves in 2015, produced by the collision of two black holes more than 1 billion light-years away, observatories including LIGO in the United States, Virgo in Europe, and Kagra in Japan have detected dozens of additional events, including collisions between black holes, collisions between neutron stars, and mixed collisions between the two. Each detection provides an entirely independent way of studying extreme gravitational environments, separate from anything that can be learned using light alone, and future, more sensitive detectors are expected to expand this catalog significantly, potentially even detecting gravitational wave signals left over from the earliest moments after the Big Bang itself, moments that no telescope using light could ever directly observe, since they occurred before the cosmic microwave background was released. Taken together, these open questions point toward a genuinely interesting feature of modern cosmology. The broad picture, an expanding universe roughly 13.8 billion years old, containing roughly 2 trillion galaxies within its observable portion, built from a small percentage of ordinary matter alongside much larger amounts of dark matter and dark energy, is well supported by an enormous body of independent evidence gathered using multiple completely different techniques. But the fine details, exactly what dark matter and dark energy actually are, exactly how quickly the universe is expanding today, and exactly how the earliest galaxies formed and grew so quickly, remain active, unresolved areas of research, with new data arriving from multiple major instruments essentially every year. There is another layer to this story worth exploring in more detail, because nearly every galaxy astronomers have studied, including our own, appears to host an enormous black hole at its very center, the one at the heart of the Milky Way, named Sagittarius, a star, contains a mass equivalent to about 4 million times the mass of our Sun, compressed into a region not much larger than the orbit of Mercury around our own Sun. Despite that staggering mass, Sagittarius A star is relatively quiet compared to many supermassive black holes found at the centers of other galaxies, since it is not currently pulling in large amounts of surrounding gas and dust. In 2019, an international collaboration called the Event Horizon telescope released the first ever direct image of a black hole's silhouette, capturing the supermassive black hole at the center of a galaxy known to astronomers as M87, located about 55 million light-years away, with a mass around 6.5 billion times that of our Sun. In 2022, the same collaboration released a comparable image of Sagittarius A star itself, confirming decades of indirect evidence based on tracking the orbits of stars swinging closely around the galactic center, that an object of that mass really does exist exactly where models predicted. These images are not photographs in the traditional sense, A black hole itself emits no light, since nothing, not even light, can escape from within its event horizon, the boundary beyond which the gravitational pull becomes inescapable. What the Event Horizon Telescope actually captured was the glowing ring of superheated gas swirling around the black hole just outside that boundary, with a dark central shadow cast by the black hole itself, exactly matching the shape predicted by Einstein's general theory of relativity more than a century earlier. The fact that a theory developed in 1915, using nothing but mathematics and thought experiments, correctly predicted the appearance of an object imaged for the first time more than 100 years later, remains one of the more striking confirmations in the history of physics. The relationship between a galaxy and its central supermassive black hole appears to run deeper than simple coincidence. Observations across many galaxies show a consistent correlation between the mass of a galaxy's central black hole and the mass of the surrounding bulge of stars, suggesting that galaxies and their central black holes grow together, influencing each other's development over cosmic time through processes that are still being actively studied. Some of the unusually bright, compact objects recently identified by the James Webb Space Telescope in the very early universe may represent an early, poorly understood phase of this same coevolution, when the first galaxies and their central black holes were growing rapidly and simultaneously, shortly after the earliest stars had formed. It is worth pausing on just how different the physics of the very small looks compared to everything described so far. An atom measures roughly 1/10,000,000th of a meter across, its structure dominated by empty space in almost the same proportion that a galaxy is dominated by empty space between its stars. If the nucleus of a hydrogen atom were scaled up to the size of a basketball, the single electron orbiting it would, on average, be found roughly 2.5 miles away, with essentially nothing but empty space, or more precisely, a quantum mechanical probability field filling everything in between. This structural similarity, vast emptiness punctuated by tiny, dense concentrations of matter, repeating at scales separated by dozens of orders of magnitude, from atomic nuclei to solar systems to galaxies to galaxy clusters, is one of the more striking patterns that emerges once you actually compare the geometry of the very small to the geometry of the very large. Even though the underlying physical forces governing each scale are completely different, none of this similarity implies any kind of literal nested universe, where atoms secretly contain tiny galaxies. A popular but scientifically unsupported idea sometimes floated in casual conversation. The actual physics of atomic structure, governed by quantum mechanics and the electromagnetic force, has essentially nothing in common mechanistically with the physics of galactic structure, governed by gravity acting across much larger masses and distances. The visual similarity is a coincidence of proportion, not evidence of any deeper connection, though it remains a genuinely useful way to build intuition for just how much empty space dominates structures at every scale we have been able to measure. From the atomic to the cosmic dot, return to the question of exoplanets for a moment, since it ties directly back into the scale of habitable environments across those 2 trillion galaxies. Astronomers have confirmed more than 5,000 exoplanets to date, using primarily two detection methods. The transit method looks for a tiny, periodic dimming in a star's brightness, caused when a planet passes directly between that star and our telescopes, blocking a small fraction of its light on a regular, repeating schedule. The radial velocity method instead looks for a subtle, periodic wobble in a star's position, caused by the gravitational tug of an orbiting planet pulling the star very slightly back and forth. Combining both methods allows astronomers to estimate not just a planet's orbital period and distance from its star, but often its approximate size and mass as well. Among these confirmed exoplanets, a smaller subset orbit within what astronomers call the habitable zone, the range of distances from a star where surface temperatures on a rocky planet would theoretically allow liquid water to persist. Considered an important, though not the only, condition generally associated with the kind of chemistry that supports life as we currently understand it, the James Webb Space Telescope has begun directly analyzing the atmospheres of some of these planets, using a technique called transmission spectroscopy, which examines starlight filtering through a planet's atmosphere during a transit, to detect the chemical fingerprints of specific molecules such as water vapor, carbon dioxide, or methane. In principle, this same technique could eventually detect what astronomers call biosignatures, atmospheric chemical combinations that would be difficult to explain without biological activity, though no confirmed biosignature detection has been announced to date, and several candidate signals reported in recent years have required careful follow-up analysis before being confirmed or ruled out. A useful, if deliberately speculative framework for thinking about the odds of life elsewhere is something called the Drake equation, first proposed by astronomer Frank Drake in 1961. It is not intended as a precise calculation, since several of its terms remain essentially unknown, but rather as a structured way of breaking down a very large question into smaller, individually more tractable pieces. The equation multiplies together factors including the average rate of star formation in a galaxy, the fraction of stars with planets, the average number of potentially habitable planets per star, the fraction of those planets where life actually develops, the fraction where that life develops intelligence, the fraction of intelligent civilizations that develop detectable technology, and finally the average length of time such a civilization remains detectable before either advancing beyond detectable signals or ceasing to exist, depending on which estimates you plug into each term. The final result can range from an essentially guaranteed abundance of civilizations across the galaxy to an estimate suggesting we might be entirely alone within the Milky Way. The honest scientific answer at present is that several of these terms remain genuinely unconstrained by direct evidence, which is exactly why ongoing exoplanet atmosphere surveys, along with dedicated radio and optical searches for artificial signals, remain active and scientifically motivated areas of research. Rather than settled questions, it helps, at this point, to step back and lay out the broader timeline connecting everything described so far, from the earliest moments after the Big Bang to the present day. In the first fraction of a second, the universe is thought to have undergone the extremely rapid expansion described earlier as inflation. In the following few minutes, as the universe cooled from its initial extreme temperature, protons and neutrons combined to form the very lightest atomic nuclei, mostly hydrogen and helium, in a process called primordial nucleosynthesis, setting the basic chemical ingredients that would later go on to form the very first stars. For the next roughly 380,000 years, the universe remained an opaque, glowing plasma, until recombination allowed light to travel freely for the first time, producing the cosmic microwave background described earlier. For a period after that, sometimes called the Cosmic Dark Ages, the universe contained no stars at all, just slowly cooling gas gradually clumping together under gravity. The first stars are thought to have ignited somewhere between 100 million and 400 million years after the Big Bang, early massive stars burning through their fuel quickly and dying in supernova explosions that seeded the surrounding gas with the first heavier elements. Over the following few billion years, galaxies gradually assembled from these early star-forming regions, merging and growing through repeated collisions, roughly following the same processes described earlier for the eventual Milky Way and Andromeda merger. Our own solar system did not form until relatively late in this timeline, condensing from a cloud of gas and dust roughly 4.5 billion years ago, meaning more than 9 billion years of cosmic history had already unfolded before our sun and planets even existed. From that point forward, the story becomes considerably more familiar. Earth's crust cooled, oceans formed, and the earliest evidence of life on our planet appears in the geological record, starting somewhere around 3.5 to 4 billion years ago. Though the exact timing and mechanism by which non-living chemistry first organized into something recognizably alive remains one of the genuinely open questions in origin of life research, distinct from the cosmological questions described earlier but connected to them through the same chain of stellar nucleosynthesis that produced the carbon, nitrogen, oxygen, and phosphorus needed for the chemistry of life as we understand it. For roughly the next 3 billion years, life on Earth remained exclusively microbial, single-celled organisms slowly reshaping the planet's atmosphere and oceans, most notably through the gradual buildup of oxygen produced by early photosynthetic bacteria, an event geologists call the Great Oxidation Event, which occurred roughly 2.4 billion years ago and fundamentally altered the chemistry of Earth's atmosphere in ways that eventually made complex, oxygen-breathing life possible. Complex, multicellular life did not appear until much later, generally placed somewhere around 600 million years ago, followed by the rapid diversification of animal body plans during the Cambrian period, roughly 540 million years ago. Dinosaurs dominated terrestrial ecosystems for well over 100 million years, before an asteroid impact around 66 million years ago triggered a mass extinction event that eliminated the majority of large dinosaur species, clearing ecological space that allowed mammals to diversify and eventually, tens of millions of years later, produce the branch of primates that would eventually include modern humans. Anatomically modern humans are generally estimated to have appeared somewhere in the range of 200,000 to 300,000 years ago, meaning that if you compressed the entire 13.8 billion year history of the universe into a single calendar year, all of recorded human history, every war, every empire, every scientific discovery described in this narration, would fit into the final few seconds before midnight on December 31st. That kind of compression exercise is worth taking seriously rather than treating as a throwaway rhetorical flourish, because it clarifies something important about the actual relationship between human timescales and cosmic timescales. It is not simply that the universe is old. It is that essentially all of the interesting cosmic history described throughout this explanation, the formation of galaxies, the death and rebirth of stars that seeded the elements now present in your body, the slow assembly of the local group, the ongoing acceleration of cosmic expansion, unfolded across timescales so much longer than any human lifespan, or even the entire span of recorded civilization. That direct human experience provides essentially no useful intuition for any of it. Every one of the numbers described in this explanation, 100,000 light-years, 2 trillion galaxies, 13.8 billion years, has to be understood indirectly, through careful measurement and mathematics, rather than through anything resembling direct sensory experience, which is exactly why building an accurate mental picture of the universe took humanity so long, and why getting it right required the specific combination of precise instruments, careful mathematics, and patient, repeated observation described throughout this explanation. it is worth returning, briefly, to the practical side of how all of these enormous distances are actually measured, since the methods themselves are almost as interesting as the results they produce. For relatively nearby stars, astronomers use a technique called parallax, which relies on the same basic principle you can demonstrate yourself by holding a finger up at arm's length and alternately closing one eye and then the other. Your finger appears to shift position slightly against the background, purely because your two eyes are viewing it from slightly different positions. Astronomers apply the same logic on a much larger scale, observing a nearby star's apparent position against more distant background stars from 2 points in Earth's orbit around the Sun 6 months apart, then using the known diameter of that orbit and simple trigonometry to calculate the star's distance from the size of its apparent shift. This method works reliably for stars within a few thousand light-years, beyond which the apparent shift becomes too small to measure precisely. Even with modern space-based instruments such as the European Space Agency's Gaia satellite, specifically designed to measure these tiny shifts with extraordinary precision across more than 1 billion stars, for distances beyond the reach of parallax, astronomers rely on what are called standard candles, objects whose true brightness can be calculated independently of their apparent brightness as seen from Earth, allowing distance to be calculated from the difference between the two. Cepheid variable stars, mentioned earlier in connection with Hubble's discovery of Andromeda's true distance, serve this purpose for galaxies within roughly 100 million light-years, since their pulsation period reliably indicates their true luminosity. For galaxies far beyond that range, astronomers instead rely on Type 1, a supernova, a specific class of stellar explosion that occurs when a particular type of dead star, called a white dwarf, accumulates enough additional mass from a companion star to cross a well-defined physical threshold and detonate in a thermonuclear explosion of remarkably consistent total brightness. Because that explosion brightness is so consistent from one occurrence to another, comparing a given supernova's true brightness to its apparent brightness as observed from Earth allows astronomers to calculate its distance, even for supernova occurring in galaxies billions of light-years away, far beyond the reach of any other direct distance measuring technique. This chain of overlapping techniques, parallax calibrating Cepheids, Cepheids calibrating supernova, is what astronomers refer to as the cosmic distance ladder, and it forms the entire observational foundation, underlying every distance figure described throughout this explanation, underlying the supernova method, and underlying Hubble's law more generally, is a phenomenon called worth explaining clearly since it comes up constantly in cosmology without always being unpacked. Light behaves in some ways like sound, just as the pitch of a passing ambulance siren drops as it moves away from you, a phenomenon called the Doppler effect. The wavelength of light from an object moving away from an observer stretches out, shifting its color slightly toward the red end of the visible spectrum. The faster an object recedes, the more pronounced this redshift becomes, because Hubble's law establishes that more distant galaxies recede faster. Measuring a distant galaxy's redshift provides a direct, quantifiable way to estimate its recession velocity, and from that, using the known relationship between velocity and distance, its approximate distance from Earth. For the most distant galaxies detected by the James Webb Space Telescope, redshift values are high enough that visible light emitted by those galaxies has been stretched all the way into the infrared portion of the spectrum by the time it reaches Earth, which is precisely why an infrared optimized telescope like Webb was necessary to detect them in the first place, since older telescopes optimized primarily for visible light simply could not see them clearly. It is worth being precise about a subtlety here, because it is commonly misunderstood. Cosmological redshift, the kind used to measure distances to remote galaxies, is not identical to the simple Doppler effect used to explain a passing ambulance. A passing ambulance is physically moving through the surrounding air. A distant galaxy, receding due to cosmic expansion, is not necessarily moving through space in the same sense. Instead, the space between the galaxy and Earth is itself expanding, stretching the wavelength of light as it travels across that expanding space over billions of years. The practical mathematics work out similarly enough that astronomers can use redshift as a reliable distance indicator either way. But the underlying physical mechanism, expanding space itself rather than an object simply moving through static space, is an important distinction for understanding concepts described earlier, including the fact that some very distant galaxies show recession velocities that appear to exceed the speed of light, without actually violating relativity. Return, for a moment, to the cosmic web and the large-scale surveys responsible for mapping it. One of the most influential projects in this area, the Sloan Digital Sky Survey, began operations in 2000 and has since measured the precise position, distance, and other properties of more than 1 million galaxies, along with detailed spectra for many of them, allowing researchers to construct genuinely three-dimensional maps of galaxy distribution across large volumes of the observable universe, rather than the flat, two-dimensional maps that earlier, less ambitious surveys were limited to. It was largely through this kind of systematic three-dimensional mapping that the filament, wall, and void structure of the cosmic web first became clearly visible. Rather than remaining a theoretical prediction inferred indirectly from more limited data, more recent surveys have pushed this mapping effort considerably further. The DESI project mentioned earlier, in addition to its work constraining dark energy, has produced what is currently the largest three-dimensional map of galaxy positions ever assembled, spanning several billion light-years and incorporating spectroscopic data, meaning detailed measurements of a galaxy's light broken down by wavelength for tens of millions of individual galaxies. Upcoming surveys from the Vera Rubin Observatory and the Euclid Space Telescope are each expected to add billions of additional galaxies to similar catalogues over the next several years, continuing to refine researchers' understanding of exactly how matter, both visible and dark, is distributed across the largest observable scales, and providing an increasingly detailed observational test of the specific predictions made by current models of cosmic structure formation. It is genuinely remarkable, when you consider it directly, that essentially every specific number described throughout this explanation, 100,000 light-years for the width of the Milky Way, 400 billion stars within it, 2 trillion galaxies across the observable universe, 13.8 billion years for the age of the universe itself, 93 billion light-years for its current observable diameter, has been independently measured, cross-checked, and refined using multiple different techniques developed across more than a century of astronomical research, rather than simply asserted or estimated casually. Each of these figures represents the accumulated result of parallax measurements taken from opposite sides of Earth's orbit, pulsating stars calibrated against known physical relationships, exploding white dwarfs used as consistent brightness references, satellite measurements of ancient background radiation precise to millionths of a degree and repeated, systematic surveys cataloging the positions of literally millions of individual galaxies. The scale of the universe is not a matter of imaginative speculation. It is the accumulated result of an enormous, ongoing, carefully cross-checked measurement project that has occupied astronomers for well over 100 years and continues actively today. it is worth briefly returning to Earth itself and to the Sun, since both have their own long-term trajectory within this larger cosmic story. Our Sun is a middle-aged star, about 4.5 billion years into what is expected to be roughly a 10 billion year total lifespan as a stable, hydrogen-fusing star. In approximately 5 billion years, once the hydrogen fuel in its core is significantly depleted, the Sun is expected to expand into what astronomers call a red giant, its outer layers swelling outward to a size that will likely engulf the orbits of Mercury and Venus, and possibly Earth as well, depending on exactly how much mass the Sun sheds during that expansion phase. Eventually, after shedding its outer layers entirely, the Sun's core will contract into a dense, slowly cooling remnant called a white dwarf, a fate shared by the vast majority of stars similar to our own in mass. This is not an imminent concern on any human timescale, since it remains billions of years away, but it is a useful reminder that even stars, which feel permanent and unchanging across a human lifetime, follow their own long developmental arc, born from collapsing gas clouds, living for billions of years through nuclear fusion, and eventually dying in ways that scatter their material back into the surrounding galaxy, material that may eventually be incorporated into future generations of stars and planets, continuing the same cycle of stellar nucleosynthesis described earlier in connection with the origin of the elements in your own body. Bring all of these individual pieces back together, and a coherent, if genuinely difficult to fully internalize, picture of cosmic scale emerges. You exist on a rocky planet orbiting a fairly ordinary star, one among roughly 400 billion stars distributed throughout a galaxy spanning 100,000 light-years, itself one of roughly 50 galaxies gravitationally bound together in a local group spanning 10 million light-years, which is itself one small piece of the Laniakea supercluster, spanning roughly 500 million light-years and containing more than 100,000 galaxies, which is itself one node within a cosmic web of filaments, walls, and voids extending across the entire 93 billion light-year diameter of the observable universe, a region containing an estimated 2 trillion galaxies in total, all of it expanding and accelerating in that expansion, due to a form of energy that makes up the majority of the universe's total content but whose fundamental nature remains only partially understood. None of these numbers are exaggerations, dramatized for effect, or rounded up for impact. They represent the best current measurements available, produced using overlapping, independently verified techniques refined across more than a century of careful astronomical observation, and they will likely continue to be refined, and in some cases revised, as new instruments like the Vera Rubin Observatory, the Euclid Space Telescope, and the Nancy Grace Roman Space Telescope begin returning data over the next several years. Some specific figures described in this explanation, particularly the precise total galaxy count and the precise strength and behavior of dark energy over cosmic time, are genuinely expected to be updated, potentially significantly, as that new data arrives. What will not change is the broader structure of the picture itself. A universe built from an initial hot, dense state nearly 14 billion years ago, expanding and cooling ever since, organizing its matter first into the earliest stars and galaxies, then into increasingly large gravitationally bound structures, all embedded within an ongoing, accelerating expansion whose ultimate long-term fate remains an open, actively researched question. Somewhere within that structure, on one particular planet, orbiting one particular star, a species that evolved to track food and predators across a comparatively tiny stretch of an African landscape has across only the last few hundred years of its several 100,000-year history, worked out essentially everything described throughout this explanation, using nothing more than light, careful measurement, and an accumulating, cross-checked body of evidence. That is where current research genuinely stands. Not with a settled, finished picture, but with a remarkably well-supported broad framework, still being actively refined at its edges by real instruments, collecting real data right now, aimed at resolving specific, well-defined open questions about the exact nature of dark matter, the exact behavior of dark energy over cosmic time, the surprising speed at which the earliest galaxies apparently formed, and the precise numerical rate at which the universe is expanding today. Each of those questions has a dedicated team of researchers and, in several cases, a dedicated space telescope or ground-based observatory built specifically to help answer it, with results expected to arrive steadily over the coming decade. The universe described throughout this explanation is not a finished story. It is an active, ongoing measurement, still being carried out, one galaxy, one supernova, one gravitational wave detection at a time. It is worth taking a closer look at galaxy classification itself, since not every galaxy shares the spiral structure of the Milky Way or Andromeda. Astronomers generally sort galaxies into three broad categories. First proposed by Edwin Hubble in the 1920s and still used, with modifications, today. Spiral galaxies, like our own, feature a flattened rotating disk with distinct spiral arms, typically containing active star formation and a central bulge of older stars. Elliptical galaxies, by contrast, appear as smooth, rounded collections of stars without obvious spiral structure, generally containing older stellar populations and comparatively little ongoing star formation. Since much of their available gas was used up earlier in their history or stripped away during past galactic mergers, the eventual merger of the Milky Way and Andromeda, described earlier, is expected to produce exactly this kind of elliptical remnant. A third category, irregular galaxies, includes everything that does not fit neatly into either the spiral or elliptical categories, often the result of gravitational disruption from a close encounter with another galaxy, or simply galaxies too small and too chaotic in structure to have settled into either of the more organized forms. Within actively star-forming spiral galaxies, some of the most visually striking objects are stellar nurseries, enormous clouds of gas and dust where gravity is actively collapsing material into new stars. One of the most photographed examples, a structure within the Eagle Nebula, informally called the Pillars of Creation, showcases towering columns of gas roughly 4 to 5 light-years tall, within which dense knots of material are gradually collapsing under their own gravity to ignite new stars. Observations using different wavelengths of light reveal different aspects of these structures. Visible light observations of the kind captured by the Hubble Space Telescope show the dense, opaque outer surface of the gas columns, silhouetted against the glow of nearby young stars. Infrared observations, of the kind the James Webb Space Telescope specializes in, can penetrate much of that obscuring dust, revealing the newly forming stars embedded within the pillars themselves, otherwise hidden from view in visible light. Studying regions like this provides direct, observable evidence of the same star formation process that, applied across billions of years and hundreds of billions of stars, built the entire stellar population of the Milky Way described earlier in this explanation. It is also worth revisiting, one final time, exactly how much scientific caution should be applied to the multiverse and eternal inflation concepts described earlier, since they tend to generate more public fascination than almost any other topic in cosmology, often disproportionate to their actual observational support. The core inflation theory itself, describing a brief period of extremely rapid expansion in the earliest fraction of a second after the Big Bang, is well supported, since it successfully explains several independently observed features of the universe, including its large-scale flatness and the remarkable uniformity of the cosmic microwave background, the extension of that theory into eternal inflation, and from there into a genuine multiverse of causally disconnected regions, follows logically from certain specific versions of inflation theory, but is considerably harder to test directly, since by definition, any other universe produced this way would lie forever beyond our observable horizon, with no light, no gravitational wave, and no physical signal of any kind able to reach us from it under standard physical assumptions. Responsible science communication on this topic generally distinguishes clearly between the well-tested core theory and its more speculative extensions, a distinction worth preserving here as well, rather than treating every version of the multiverse concept as equally well established just because it emerges from otherwise credible theoretical physics. There is one more counterintuitive physical effect worth explaining before drawing this all together, because it directly affects how astronomers interpret some of the most distant observations described throughout this explanation. Einstein's theory of relativity establishes that time itself does not pass at a fixed, universal rate for every observer. Instead, the rate at which time passes depends on an observer's relative motion and on the strength of the gravitational field they are for everyday purposes here on Earth. These effects are so small they are essentially undetectable without extremely precise atomic clocks, though they are large enough that GPS satellites, which experience both a different velocity and a different gravitational field than observers on Earth's surface, require constant, carefully calculated corrections to keep their onboard clocks synchronized with clocks on the ground, corrections that, if ignored, would cause GPS positioning errors to accumulate at a rate of several miles per day at cosmological distances. A related effect called cosmological time dilation becomes directly observable, because distant galaxies are receding from us due to the expansion of space. Physical processes occurring within them, such as the rise and fall in brightness of a distant supernova explosion, appear to unfold more slowly from our perspective on Earth than they would to an observer located within that distant galaxy itself, stretched out in direct proportion to the galaxy's radius. Astronomers have directly measured this effect by tracking the brightness curves of distant Type 1, a supernova, the same standardized stellar explosions used earlier as standard candles for distance measurement, and confirming that their brightness changes unfold more slowly, exactly matching the predictions of an expanding universe, providing yet another independent line of evidence supporting the same basic expansion picture described throughout this explanation, arrived at through an entirely different observational method than Hubble's original velocity measurements or the more recent cosmic microwave background data, bringing this all the way back to where this explanation began, sitting still on a planet moving at 670,000 miles per hour, orbiting a fairly ordinary star among 400 billion others, embedded within a galaxy spanning 100,000 light-years, itself one small piece of a local group, and ultimately a cosmic web extending across roughly 2 trillion galaxies within the observable universe, is not simply an interesting fact to be marveled at once and then set aside. It is the specific, carefully measured, actively researched context within which every other question in astronomy and cosmology is currently being pursued. Researchers are not simply confirming numbers already established decades ago. They are actively refining the exact rate of cosmic expansion, actively searching for the physical nature of dark matter, actively investigating why the earliest galaxies appear to have formed faster and grown larger than older models predicted, and actively mapping an increasingly detailed three-dimensional picture of exactly how matter, both visible and invisible, is distributed across the largest structures the universe has to offer. None of this requires exaggeration or dramatized language to be genuinely remarkable. The measured, cross-checked, independently verified scale of the observable universe, 2 trillion galaxies, 93 billion light-years across, 13.8 billion years old, is already, on its own terms, difficult to fully internalize, and stands as one of the more significant achievements of scientific measurement in human history. Understanding it clearly, piece by piece, method by method, measurement by measurement, is considerably more interesting, and considerably more durable than any dramatized retelling could ever be. It is worth adding a closing thought about why this particular subject tends to stay interesting rather than becoming a simple list of facts to be memorized once and forgotten. Every specific number described throughout this explanation exists because a particular team of researchers, often working across multiple countries and multiple decades, built a specific instrument, collected a specific dataset, and applied a specific mathematical technique to extract that number from raw observational data. The width of the Milky Way emerged from parallax measurements and variable star calibration. The age of the universe emerged from detailed analysis of the cosmic microwave backgrounds, tiny temperature fluctuations. The existence of dark matter emerged from measuring galaxy rotation speeds and later, from the separated mass distributions visible in colliding galaxy clusters like the Bullet cluster. The acceleration of cosmic expansion emerged from tracking the brightness of distant exploding stars. Each of these results could, in principle, have come out differently, and in a few cases, including the ongoing Hubble tension and the recent hints of possibly weakening dark energy from the DESI survey, current data genuinely does not yet match the simplest version of the standard model perfectly, leaving open the possibility that some meaningful revision to current cosmological understanding may still be needed. That openness is not a weakness in the science. It is closer to the opposite. A framework detailed enough and tested against enough independent lines of evidence to identify its own specific points of tension, its own specific unresolved discrepancies, is a framework that is actively being checked against reality rather than simply asserted and left unexamined. The next decade of results from the Vera Rubin Observatory, the Euclid Space Telescope, the Nancy Grace Roman Space Telescope, continued observations from the James Webb Space Telescope, and expanding gravitational wave detection networks are each specifically positioned to test one or more of these open questions directly, using data that, in most cases, does not yet exist but is actively being collected right now. Whatever those results show, they will either reinforce the broad picture described throughout this explanation, or reveal a specific, well-defined place where that picture needs to be revised. And either outcome would represent genuine scientific progress rather than a failure of prior understanding. That is, ultimately, the honest state of current knowledge about the scale of the universe, vast beyond ordinary human intuition, measured with a level of precision and cross-verification that took more than a century to build, and still, in specific and well-identified ways, actively being refined by researchers working right now, using instruments built specifically to close the remaining gaps in a picture that is already, by any reasonable standard, one of the most remarkable achievements of careful, patient, methodical human observation. There is a specific practical reason this subject rewards revisiting rather than treating as settled after a single explanation. Cosmology, more than most branches of science, depends on a small number of foundational measurements that ripple outward to affect nearly every other number in the field. If the precise value of the universe's current expansion rate shifts even slightly as new data arrives from Rubin, Euclid, or Roman, that shift does not stay isolated. It propagates outward into revised estimates of the universe's total age, revised distances to galaxies calibrated against that expansion rate, and revised timelines for exactly when the earliest stars and galaxies must have formed in order to match everything observed since. This interconnectedness is part of why the Hubble tension described earlier has drawn so much sustained research attention. It is not simply a minor discrepancy between two research groups. It is a small crack in a load-bearing wall of the entire cosmological framework, and resolving it correctly matters for far more than the single number directly in question. The same is true of the unexpectedly massive and unexpectedly early galaxies discovered by the James Webb Space Telescope. If those observations hold up under continued scrutiny, and current evidence increasingly suggests they will, they do not simply add a few interesting outlier objects to an existing catalogue. They require astronomers to reconsider how efficiently gas can collapse into stars in the early universe, how quickly the first supermassive black holes could plausibly grow, and how the standard timeline connecting the cosmic microwave background to the first galaxies needs to be adjusted to accommodate structures that appear to have formed and matured faster than earlier models allowed. Science of this kind rarely moves through single, isolated discoveries. It moves through exactly this kind of cascading revision, where one carefully verified anomaly forces a broader reassessment across an entire connected framework of theory and evidence. This is, in the end, why the picture described throughout this explanation is worth understanding in its actual scientific detail, rather than as a simple collection of impressive numbers to be repeated without context. 2 trillion galaxies, 400 billion stars in our own galaxy alone, 93 billion light-years of observable diameter, 13.8 billion years of cosmic history, are not simply facts meant to produce a moment of awe and then be set aside. They are the current, best available output of an enormous, ongoing, carefully cross-checked measurement project built from parallax angles, pulsating variable stars, exploding white dwarfs, ancient background radiation, gravitational lensing, and direct gravitational wave detection. A project that has occupied multiple generations of researchers, continues to employ some of the most sophisticated instruments ever constructed, and remains, in several specific and well-defined ways, genuinely unfinished. Understanding where that project currently stands, including exactly which parts remain settled and which parts remain actively contested, is a considerably more durable and more scientifically honest way to appreciate the scale of the universe than any single dramatic number ever could be on its own.